Good morning, all. We, the first year mathematics students of Sacred Heart College, Devara, has come up with our presentation of the seminar on the topic Astrophysics. Particularly, we have selected the topic Neutron star and Supernova Explosion. We would sincerely thank our guide and our professor, Dr. Pius Augustine, for his constant support and making all our doubts clear. Let me move on to the contents. I will now introduce you to our teammates and the respective topics they are going to deal with. First of all, Anju Joshi will be dealing with supernova. Then Donna Davis with the types and impacts of supernova explosion. Joel Jijo will continue with examples and naming of the supernova. Krishna S will be dealing with types and formation of neutron star. And finally, Krishna Harikumar will be dealing with structure and properties of neutron star. So let's move on to the respective presentations. So, what is a supernova? A supernova is the biggest explosion that humans have ever seen. Each blast is the extremely bright, super powerful explosion of a star. It is the largest explosion that takes place in space. This transient astronomical event occurs during the last evolutionary stages of a massive star or when a white dwarf is triggered into runaway nuclear fusion. It is the name given to the cataclysmic explosion of a massive star at the end of its life. It can emit more energy in a few seconds than our sun will radiate in its lifetime of billions of years. It is a star's colossal explosion at the end of its life, potentially outshining its entire galaxy. What causes a supernova? Supernovas are of two types. The first type of supernova is caused by the last hurrah of a dying massive star. This happens when a star, at least 5 times the mass of our Sun, goes out with a fantastic bang. Also, massive stars burn huge amounts of nuclear fuel at their cores or centers. This produces tons of energy, so the center gets very hot. Heat generates pressure, and the pressure created by a star's nuclear burning also keeps that star from collapsing. Now the question arises, what holds a star together? A star is a balance between two opposite forces. The star's gravity tries to squeeze the star into the smallest, tightest ball possible. But the nuclear fuel burning in the star's core creates strong outward pressure. This outward push resists the inward squeeze of gravity. When a massive star runs out of fuel, it cools off. This causes the pressure to drop. Gravity wins out and the star suddenly collapses. Imagine something 1 billion times the mass of star collapsing in 15 seconds. The collapse happens so quickly that it creates enormous shock waves that cause the outer part of the star to explode. Usually, a very dense core is left behind, along with an expanding cloud of hot gas called a nebula. A supernova of a star more than about 10 times the size of our Sun may leave behind the densest objects in the universe, that is, black holes. A second type of supernova can happen in systems where two stars orbit one another and at least one of those stars is an Earth sized white dwarf. A white dwarf is what's left after a star the size of our Sun has run out of fuel. If one white dwarf collides with another or pulls too much matter from its nearby star, the white dwarf can explode. You may imagine how bright are supernovas. As supernovas are the massive explosion of stars, they are very bright. These spectacular events can be so bright that they outshine their entire galaxies for a few days or even months. They can be seen across the universe. A question may now pop up in your mind: how common are supernovas? This phenomenon is complex and does not happen very often. Astronomers believe that about 2 or 3 supernovas occur each century in galaxies like our own Milky Way. Because the universe contains so many galaxies, astronomers observe a few hundred supernovas per year outside our galaxy. Space dust blocks our view of most of the supernovas within the Milky Way galaxy. You can think of something now. To get these much information of supernovas, who studied it and what made us find all these things? Let us look into the question: how do scientists study supernovas? NASA scientists use a number of different types of telescopes to search for and then study supernovas. One example is the NuSTAR, which is Nuclear Spectroscopic Telescope Array mission, which uses X-ray vision to investigate the universe. NuSTAR is helping scientists observe supernovas and young nebulas to learn more about what happens leading up to, during, and after these spectacular blasts. You may naturally think now, what can we learn from supernovas? Well, it's not us, but the scientists have learned a lot about the universe by studying supernovas. They use the second type of supernova, that is, the kind involving white dwarfs, like a ruler to measure distances in space. They also have learned that stars are the universe factories. Stars generate the chemical elements needed to make everything in our universe. At their cores, stars convert simple elements like hydrogen into heavier elements. These heavier elements, such as carbon and nitrogen, are the elements needed for our life. Only massive stars can make heavy elements like gold, silver, and uranium. When explosive supernovas happen, stars distribute both stored up and newly created elements throughout space.
Thank you, Anju. Hi all, I am Donna Davis and I am dealing with the topic the types and impacts of supernova. A supernova is a star's colossal explosion at the end of its life, potentially outshining its entire galaxy. A supernova happens where there is a change in the core or center of a star. One of the star's carbon oxygen white dwarfs steals matter from its companion star. Eventually, the white dwarfs accumulate too much matter. Having too much matter causes the star to explode, results in a supernova. Types of supernova. Do you know how supernovas are classified? Scientists classify different types of supernova by the emitted light signatures called spectra. These show what elements the original star created and thus released into the space after it exploded. Supernova is mainly classified into two types based on the presence of hydrogen spectrum. Type 1 supernova and type 2 supernova. Type 1 supernova consists of three types: type 1a supernova, type 1b supernova, and type 1c supernova. In type 1a supernova, their spectrum show with little hydrogen and a lot of carbon. They also show silicon, calcium, and elements up to iron due to the fusion during the intensive explosion. Astronomers believe this type of supernova results from a white dwarf. Type 1b supernova contain very little hydrogen but also show helium. Scientists think this type of supernova results from the death of a star at least 25 times the Sun's mass. Type 1c supernova contain a very little hydrogen or helium. This type is also formed like the type 1b supernova. Collectively, type 1 supernova is called this triple core collapse supernova. Type 2 supernova has a lot of hydrogen and helium in their spectrum. Astronomers think this type results from the death of a star larger than 8 times our Sun's mass. Based on light curve, they are divided into two, type 2L supernova and type 2P supernova. Type 2L supernova show a steady decline of light curve. Meanwhile, type 2P display a period of slower decline in their light curve followed by a normal decay. This type follows the explosion. Based on emission lines, it is classified into type 2N supernova. Type 2 supernova are called the core collapse supernova. Now let's look into a flowchart which explains how supernova explodes. In the case of type 1a supernova, star like Sun expands to red giant and shed out their outer layers. Then it cools and contracts to white dwarf. But if it can accelerate mass from a binary partner, it may pass 1.4 solar masses and suddenly explode into type 1a supernova. It happens within 10 billion years. In the case of type 2 supernova, massive stars of mass more than 8 solar masses shed out their layers and form blue combat star. Then it explodes to form type 2 supernova. Sometimes these massive stars directly expand to red giant and explode to form type 2 supernova. What happens when a supernova explodes? When a supernova explodes, this causes the pressure to drop. Gravity wins out and the star suddenly collapses. Imagine something 1 million times the mass of Earth collapsing in 15 seconds. This collapse happens so quickly that it creates anomalous shock waves that cause the outer part of the star to explode. What are the impacts of supernova explosion? The first point is source of heavy elements. Supernova are the major sources of elements in the interstellar medium from oxygen to rubidium through the theoretical abundance of the elements produced. Second point is role in stellar evolution. Remains of many supernova consist of a compact object and a rapidly expanding shock wave of material. This cloud of material seeps up surrounding interstellar medium during a free expansion phase which can last for up to 2 centuries. The next point is cosmic rays. Supernova remains might be the major source of cosmic rays. Supernova remains are thought to accelerate a large fraction of galactic primary cosmic rays, but direct evidence for cosmic ray production has only been found in a small number of remains. The next point is gravitational waves. Supernova are potentially strong galactic sources of gravitational waves, but none have so far been detected. The only gravitational wave events so far detected are from mergers of black hole and neutron star, probably the remains of supernova. The last point is effects on Earth. A near-Earth supernova is a supernova close enough to the Earth to have noticeable effects in its biosphere. Depending upon the type and energy of a supernova, it could be as far as 3000 light years away. Type 1a supernova are thought to be potentially the most dangerous if they occur close enough to the Earth. So I hope you have understand this, and this is all about mine. Now I invite Joel to continue the session.
Let us recap some facts about supernova. A supernova is a powerful and luminous stellar explosion. This is a transient astronomical event occurs during the last evolutionary stages of a massive star, or when a white dwarf is triggered into runaway nuclear fusion. The original object, called the progenitor, either collapses to a neutron star or black hole, or is completely destroyed. The word supernova was coined by Walter Wade and Fritz Zwicky in 1929. Supernova are more energetic than nova. In Latin, nova means new and referring astronomically to what appears to be a temporary new bright star. Adding the prefix super distinguishes supernovae from ordinary novae, which are far less luminous. The most recent directly observed supernova in the Milky Way galaxy was Kepler supernova, which is discovered in 1604 and also known as SN 1604. Now, before going into the nomenclature of supernova, we can look at some examples of supernovas discovered since now. SN 1987A, SN 1604, also known as Kepler supernova, SN 1006, SN 1572, SN 2006 GY, SN 2016 APS, SN 185. Supernova. Supernova discoveries are reported to the International Astronomical Union's Central Bureau for Astronomical Telegrams, which sends out a circular with the name it assigns to that supernova. We can look for an example here. SN 1987A. The name is formed from the prefix SN, which means supernova, followed by the year of discovery, suffixed with one or two letter designation. The first 26 supernova of that year are designated with the capital letter from A to Z. Afterwards, pairs of lowercase letters are used, likewise AA, AB, and so on. Hence, for example, SN 2003C designates the third supernova reported in the year 2003. Before 1885, it was named simply by the year they occurred. Since 1885, the additional letter notation has been used, even if there was only one supernova discovered that year. In SN 1885A, SN 1907A, etc. Until 1987, two-letter designations were rarely needed. Since 1988, however, they have been needed every year. Since 2000, professional and amateur astronomers have been finding several hundreds of supernovae each year. Likewise, examples in 2007, 507 supernovas were discovered. In 2008, 261, 2009, 390, 2013, 231, and likewise. And from 2016, the increasing number of discoveries has regularly led to the additional use of three-digit designations, for example in SN 2016 APS. So by this I conclude my portion. Now I invite Krishna S for the remaining portion.
I am Krishna and I am going to discuss on the topic neutron star. So first of all, we will look at what is the definition of a neutron star. A neutron star is a collapsed core of a massive supergiant star which has a total mass of between 10 and 25 solar masses. Except for black holes and some hypothetical objects like the white holes and the quark stars, neutron stars are the smallest and the densest currently known class of stellar objects. Neutron stars have a radius of the order 10 km and mass about 1.4 solar masses. The neutron stars results from the supernova explosion of a massive star combined with the gravitational collapse. Next topic is the formation of a neutron star. Any star with an initial mass of about 8 times the mass of the Sun has only the potential to produce a neutron star. As the stars evolves away from the main sequence, subsequent nuclear burning produces a core. When all the nuclear fuel in the core has been exhausted, the core is then supported by the degeneracy pressure alone. The electron degeneracy pressure is overcome and the core collapses further, the temperature soaring to over 5 × 10⁹ Kelvin. At this temperature, the ion nuclei breaks into alpha particles by high energy gamma rays. As the temperature climbs higher, the electrons and the protons combine to form the neutrons, releasing floods of neutrinos. When the densities reach nuclear density of the order 4 × 10⁻17 kg per meter cube, a combination of strong force repulsion and neutron degeneracy hold the contraction. The remnant which is left is formed as a neutron star, and if the remnant has a mass greater than about 3 times the mass of the Sun, it again further collapses to form a black hole. The newly formed neutron star retains almost its angular momentum, but the moment of inertia is sharply reduced. This is because it has only a tiny fraction of its parent's radius. Types of neutron stars. Neutron stars are of two types. First is magnetar and the second is pulsars. Magnetar. A magnetar is a neutron star with particularly strong magnetic field, about 1000 times as stronger than a normal neutron star. So far, scientists have only discovered about 30 magnetars. Next is pulsars. Most of the roughly 3000 non-neutron stars are pulsars, and the pulsars emit twin beams of radiation from their magnetic poles. The pulsars also have a strong magnetic field, but it is less stronger when compared to a magnetar.
Hello everyone, I am Krishna Harkumar. Now I would like to discuss with you here some more topics related with neutron stars. Come, let us look at the internal structure of a neutron star. The neutron star structure can be split into four main layers: outer crust, inner crust, outer core, and inner core. An outer crust, starting from the surface and with a thickness of few hundred meters, composed by atomic nuclei and free electrons. The density there is just 1 ton per cubic centimeter. The next layer is the inner crust, where free electrons form a very dense solid layer. Deeper down, there is an outer core where free electrons, neutrons, protons coexist in a nuclear soup. Fourth layer is the inner core, a mysterious zone where elementary particles behave in an unpredictable way. The inner core of the neutron star is the densest point of the observable universe and probably reaching the values of about 1 billion tons per cubic centimeter. The rigid outer crust and superfluid inner core may be responsible for the pulsar glitches, where the crust cracks or slip on the superfluid a little while. Our next topic is properties of neutron stars. Neutron stars have five basic properties: a small diameter, high density, mass and temperature, strong gravity, and strong magnetic field. Neutron stars are only several kilometers in diameter, often no more than a city. Neutron stars are extremely dense, about 10 raised to 40 times denser than water. They are at least 40% more massive than our Sun, however. The temperature inside a newly formed neutron star is from around 10 raised to 11 to 10 raised to 12 Kelvin. But this temperature of an isolated neutron star falls within a few years to around 10 raised to 6 Kelvin. This is due to the high emission of huge number of neutrinos that carry away so much energy. Neutrinos are subatomic particles actually that are very similar to electrons and are one of the most abundant particles in the universe also. The gravitational force of a neutron star is directly proportional to its mass and inversely proportional to its radius squared. Thus, neutron stars have very strong gravitational field. On the surface of a neutron star, the escape speed, that is, the speed at which you would have to travel in order to escape the gravitational field of a neutron star, is 1,50,000 km per second. Compare this to the escape speed on Earth, which is only 11.2 km per second. As I already mentioned earlier, a neutron star is not entirely composed of neutrons. It also contains some number of protons and electrons. It is those particles which are electrically charged that can produce current and therefore sustain a strong magnetic field. Now let us move on to the last topic, rotation of neutron stars and some process related to it. Neutron stars rotate rapidly after their formation due to the conservation of angular momentum. A newborn neutron star can rotate many times a second. Over time, neutron stars slow as their rotating magnetic field in effect radiate energy associated with rotation. As a result, older neutron stars may take several seconds for each revolution. This is called spin down. That is, the process of slowdown of the rotational speed of neutron stars is called spin down. When the rotational speed of neutron star increases, that process can be called spin up. For example, in the case of millisecond pulsars, they can increase their rotational speed by absorbing the orbiting matter from the companion stars. Sometimes a neutron star will undergo a glitch. What is a glitch? Glitch is a sudden small increase of its rotational speed, or simply we can say spin up. Glitches are thought to be the effect of a starquake. Starquake is very similar to earthquake and which happens when the crust of the neutron star rupture due to the slowdown of the rotation. After the starquake, the star will have a smaller equatorial radius and because angular momentum is conserved, its rotational speed will increase and thus glitches occur. And another phenomenon called anti-glitch, that is a sudden small decrease in the rotational speed or spin down, has also been reported earlier. But current neutron star models do not predict this behavior. So that's all about neutron stars. Thank you so much.